Good morning, everyone. Welcome to Brandforsk and this result webinar about limiting fire spread in large floor plan compartments with visible timber. My name is Mattias Delin, and I'm the research director here at Brandforsk. This project was funded by Brandforsk, but also by Frick in Norway and DGMR in the Netherlands. And with us today, we have Daniel Brandon and Johan Sjöström at RISE that will present this project made by many people, but especially by them. So welcome, Daniel and Johan.
Thank you.
Morning.
Thank you.
Good morning.
So tell me, Daniel, who are you?
Yes, my name is Daniel Brandon. I work at RISE since 2015. And I work mostly on fire safety of timber structures.
Right, welcome. And Johan?
Hi there. I'm a colleague of Daniel. We work in the same group, but I sit mostly in Borås, whereas Daniel is down in Skåne, working on many aspects of fire and sometimes with timber buildings together with Daniel.
Yeah, right. And when you did your tests, where were you? Skåne or Borås?
We were just
Borås.
outside of Borås at the Södra Älvsborgs Räddningstjänstförbund's place where they can practice.
Right. And this was earlier this year in May and June. You had some difficulties with the weather. What happened?
Well, it was very dry that period. We did have many quiet days, but then also some windy days. And in one test, we were quite unlucky with the wind.
Right.
But then at the end of the test series, it was dry for such a long time. We couldn't fire test. It wasn't allowed. Wasn't allowed to burn anything.
No. Right.
Yeah, until it rained, which delayed everything a bit.
Yeah. Well, such things happens, and well, you know more than most people about that because you studied forest fires as well. So, well, today we're going to learn more about your project that you did and the tests that you made, and also hear your analysis about the results. So we will get a presentation in a few minutes, and we will see you later, and we'll have questions and discussions with you. So thank you for now, and I will see you again later.
Thank you.
Some short information about Brandforsk. If you don't already know us, we have a vision, a fire-safe and sustainable society built on knowledge. We develop and communicate knowledge to limit the negative consequences of fire in the society. And we started up in 1979, and since 2019 we are a foundation. Our supporting organizations fund everything that we do, so thank you very much if you are a supporting organization, and otherwise I hope that you will become one. And this makes us a collaboration between many parts of the society. And the fundraising this year is almost 700,000 euro. So that's quite good, but we hope for more even next year. And this money is made to fund projects, research projects like this one we will learn more about in a few minutes. And also we make a great effort to really spread the results of the research projects to make it available for you to use. And we have a research school for practicing fire safety engineers, and we also have scholarships for students. Now, these are our supporting organizations this year. So thank you very much to all of you. We couldn't do this without you. And again, of course, if you're not on this list, please get on this list. So the program today is a short introduction, almost finished that, and we will get a presentation of the project. It will take about 40 minutes. And then we will have time for questions, and please ask your questions in the Q&A. So thank you for being with us today. We will now get to the presentation.
Welcome to this webinar where I discuss the results of a project named Limiting Fire Development in Large Compartments with Visible Timber Ceilings. The project is mainly funded by Brandforsk, but we also had financial and in-kind contributions by Frick and DGMR. The project team consisted of RISE, Frick, and DGMR, where RIKE did the main part of the work, but was assisted by Frick and DGMR. And as you can see, today I'm presenting on behalf of a relatively large group. During the last 20 years, mass timber structures have undergone quite a significant development, which is exemplified by this plot, which shows the global CLT production. The introduction of mass timber buildings brought new challenges, new fire safety challenges, which need to be responded to, and increasing share of the building stock indicates that it becomes more and more important to respond to those challenges. We have in recent years put a lot of focus on a research of mass timber that included fire resistance of mass timber, but also other topics beyond fire resistance, such as looking at withstanding burnout. There are some outstanding issues. One of them concerns very big compartments. And to explain the challenge, I'll show you this video of a test that was performed last year at RISE Norway led by Frick. And here we see a fire that develops, and the development is accelerated by ignition of the CLT ceiling. And this is not the first test that shows this. There have been a bunch of other tests, among which the code red tests, which were performed a year earlier. At the same time, we see an increasing number of very large compartment spaces. They're not always limited to one floor. They can consist of 3, 4, or 5, or even 6 floors. And knowing that fires can be accelerated by the contribution of mass timber itself, it becomes quite important to ensure that people still can safely evacuate the compartment, but also important that the fire brigade, the fire service intervention doesn't involve too high risks. So whether this is a concern is actually dependent on the limitations of compartment size in the buildings and the measures taken. Are there sprinklers? Are there surface treatments? And therefore, the safety in such compartments is very much dependent on the building regulations. In Europe, the building regulations are often not dependent on the construction type. That means that for a concrete building or a mass timber building, we generally have the same compartment size limits and sprinkler requirements. When we look at the regulations between countries, there we see a very significant differences in compartment size limits, but also surface requirements. And in many countries, sprinklers are not required at all. There are countries where sprinklers are not required. There is no required treatment for timber, and compartments at the same time are not limited to one floor. And whether that is a concern, I want to discuss in the next slide with this table. This shows an overview of large-scale compartment tests with mass timber exposed. And here we see the times to flashover. These numbers seem relatively low. However, I have there is a side note that I have to mention. In all of these tests, the ignition source ignited very quickly, much quicker than you would expect in normal building fires, and therefore you can probably add a few minutes to these numbers. And but even if we rely on these numbers, they are not that alarming for most compartments. If we look even in office spaces, if they're limited to one floor and not too big, we can expect when the compartment is evacuated within a few minutes, probably 2 minutes. However, when we start to build very large compartments with multiple floors, perhaps it may be required to have more time for safe evacuation. Before I go to the goals of this project, I'll just discuss the other compartment tests. So why was there a difference? Why did flashover not occur in all of these compartments, or why was flashover delayed? The code red test 3 had automatic suppression, an automatic suppression system. In this case, water mist system. In Frick test number 1, there was no ceiling impingement. The flame was actually not high enough to reach the ceiling, and that delayed ceiling ignition. And in the RISE test in Norway, there was no ceiling protrusions. And I want to dwell a bit more on that. Here we see 2 tests performed in 2005, which was at a time where CLT was barely on the market. On the left side, we see a test with a flush ceiling, a CLT ceiling, and on the right side, we had a ceiling with beams protruding from the ceiling. The fire source was 3 megawatts, which is quite significant. And the fires developed in both tests for at least the first 4 minutes. And the test with the flush ceiling, the flame extension grew for the first 4 minutes, but after that it stabilized and didn't grow any further. In the test on the right side with the protruding beams, within 4 minutes, the flame started to extend beyond the ceiling, leading to flashover 1 minute later. And in the report, instead of listing these measures, we actually wrote some text as guidance. We use this figure for that. An obvious measure that you can take is limit the compartment size. That will likely reduce the required time of egress, and it will likely reduce the challenge for the fire surface. Another measure that you can take is using sprinklers, which is quite obvious, but less obvious measures are increasing the ceiling height, which lowers the risk of ceiling ignition, and also reducing ceiling protrusions, which avoids collection of combustible gases, concentrated layer of combustible gases under the ceiling. A very common measure that is implemented in practice is using surface treatments. However, here we have some outstanding questions because there hasn't been a lot of large-scale testing with surface treatments. Surface treatments are in Europe classed using the Euroclass system, and this system uses mainly the SPI test as a basis. The SPI test has a relatively small flame of 30 kilowatts, which represents a scenario where, for example, a bin catches fire. But now we are building very large compartments with potentially high consequences, and it becomes quite reasonable to consider more severe scenarios. So what if a sofa starts burning? It doesn't need the contribution of the lining to develop, and can actually ignite other fuel as well. In such scenarios, can we still rely on treatments to limit the fire development? To answer that question, we performed this research project and we had the following goals. Assess the impact of different treatments on the sealing, flame spread rate, the external flaming, temperature development within the compartment, the tenability and risk for ignition of variable fuel. And we looked at clear surface treatments because that way you can still see the surface of the wood, and that seems to be the demand of a common demand of architects in practice. An additional goal is to assess the correlation with SBI testing. In SBI test, we measure the heat release rate and we get several values from it. In this presentation, I'll focus on the phi value, which gives an indication of the heat release rate peak, when it occurs, and how high this peak is. And the THR 600S indicates the total heat release rate at 600 seconds. I'll use both values later in this presentation to see if there is an agreement or a correlation between performances. A desirable outcome, a desirable performance for treatments would be that it limits accelerated sealing spread and limits the risk of ignition of fuel far away from the fire source. To investigate our research questions, we performed 8 compartment tests. You see an isometric drawing here on this slide. We had a compartment with 6 openings, spaced 3 meters center to center. We designed the compartment with the intent to have a severe but representative fire scenario. We started to observe real mass timber buildings for that reason, and we looked for ceiling protrusions. The most common ceiling protrusion in mass timber buildings are beams, and they typically do not exceed 600 millimeters. That also corresponds to the maximum depths in glulam beam catalogs of producers. We also looked for the distance between these beams, and those typically do not go below 2.4 meters. So we took these 2 dimensions from our small survey and implemented them in the design. Here we see the width of the compartment, which is 2.3 meters. We don't see the seating protrusion here because it's a floor plan. But before I go to the longitudinal section of the compartment, I'll explain some features of this test. On the right side, we have the compartment start, which is the side at which the fire is ignited. Here we see the fire pool. And towards the compartment end, we have thermocouple stands, and each thermocouple stand is positioned at the same location relative to the nearest opening. We also have additional ignition specimens, which were positioned 1.6 meters under the ceiling and consisted of a 20 millimeter thick spruce panel that was conditioned to be 10.5%, have a moisture content of 10.5%. We also had 5 high definition cameras, and we also had a webcam which had a much lower definition. Here we see the longitudinal section, and we see this measurement back. This was the measurement I discussed of ceiling protrusions. We don't have a beam under the ceiling, but we chose to have the distance between the ceiling and the top of the opening equal to 600 millimeters to get a representative smoke layer thickness. Under Under the fire pool, we had 4 load cells. However, we only had them in the first 2 tests, since in both tests we lost equipment and we couldn't really continue these measurements because of the high costs. Here in the ceiling, we see 2 different sections. Above the fire pool, we had a mass timber element made of CLT. But for cost efficiency further away from the compartment, we had spruce paneling, which was backed with 2 layers of OSB, and on top of that there was 50 millimeter layer of stone wool. The OSB was there to form a thermal boundary that was aiming to be representative for a thicker mass timber slab. The fuel that we used was E85, which is 85% ethanol and 15% petrol. And we had a fire pool of 1.2 by 1.2 meters. We used 95 liters of E85, and we chose this fuel based on our requirements. We wanted to have flame impingement. We wanted low sootiness to have a good visibility of the flames, but also to see the contribution or the smoke contribution of the ceiling better. We aim to have a heat release rate of 2 to 3 megawatts to represent the peak of a burning sofa. Here we see the test matrix, which is a very extensive table. For the listeners, I mainly want to highlight test R and test NC. Test R is the reference test with no treatments, so it's bare spruce that is exposed. And test NC is the non-combustible reference test, where the ceiling was covered with gypsum fiber boards. Test A to SF were all had a treated ceiling, and the treatments differed between non-expanding coating, expanding coating, and impregnated spruce paneling. Test E and F are both comprised of a timber ceiling that was protected with impregnated spruce. In test E, there was twice as much impregnation as in test F. However, we did use the same impregnation. All of these surface treatments ended up to be falling within class B S1 D0, although that wasn't the original intent when we started this project. This table also shows figure values and THR values, not the exact values, but an indication of the values to keep the products anonymous. Here we see the location at which the timber was treated, the spruce panels and also the CLT members. They were dried in this location to approximately 10% moisture content. Then they were treated, and the treatment was cured for several weeks before the test commenced. Here we see the 2 ceiling sections, the mass timber panel in the first section of the compartment, and further we see the spruce covering the OSB boards. And this is the outside of the compartment. Here we see all tests simultaneously. On the right side, we have the 2 reference tests, the untreated reference test and the non-combustible reference test. On the left side, we have test A to C, and in the middle, we have test D to F. And we see already quite early that test C had some more significant smoke development, and that test B was influenced by wind. So test B was the only test with a stationary wind that exceeded 1 meters per second. It was actually 1.1 meters per second, but the wind gusts were exceeding 2 meters per second. And even though it didn't feel like a lot of wind, you can clearly see it had a lot of influence on the smoke. Now we see that there is in test R, the untreated reference test, there is more fire development, much more than in other tests. And at this moment, the external flaming in the non-combustible reference test becomes more significant. So here at 1 minute and 28, I'll stop, and you can clearly see the difference between the reference test and the other tests. However, even though we aim to test at a very quiet moment during a day, in test R, even though there were no wind gusts approximately half an hour before the test, 1.5 minutes into the test, quite significant wind gusts started. And those wind gusts actually stirred the smoke layer, which from the inside you could see was quite plain, and now it became very turbulent, and the visibility inside of the compartment really reduced. So we know also from these videos, but also from the measurements, that the wind gusts quite significantly influenced the reference test after 1.5 minutes, which you can also see in the temperature readings. This is an example of one of the plate thermometers. In the gray regions indicate the times at which significant wind gusts occurred. And you can see that they did have an influence. They did randomize the temperature trend. And in the report, I'll discuss the measured results, the measured temperatures. We also discussed an extrapolation of the data after 1.5 minutes. But in this presentation, I won't do both. I will just cut off the results at 1.5 minutes and make for the reference test and make comparisons with the other tests. What we did see is that when there were no wind gusts, the temperatures did increase at least until the 9-minute mark. And in these calmer periods, we see that the combustion in the untreated reference test is much more significant than in other tests. Although we also saw that in test F, the fire by this time, nearing 6 minutes, had already developed quite extensively. From the inside, it looks like this. Once the wind starts to calm down, the ceiling fully ignites. And in the next slide, I'll discuss the ignition of the ignition pieces. So you can see here some flames on top of this brick. And here we see the last ignition piece that didn't ignite. So the times at which these specimens ignited is shown in this plot. Here we have the untreated reference test, and we have the non-combustible reference test, and all the tests with treated ceilings fall in between those two lines. At 4.5 meter distance from the compartment start, we see that the difference between the untreated reference test and the treated test is not that big. It's up to half a minute. It takes up to half a minute longer for these specimens to ignite. Further into the compartment, these differences become more significant. Related to that, I want to discuss the plate thermometer measurements measured by plate thermometers 1.9 meters under the ceiling, facing the ceiling, they give an indication of the fuel, of the radiation towards fuel on the floor. I'll start with opening 1. Here we see that the untreated reference test and the treated tests follow the same trend for approximately 2 minutes and then start to deviate. However, the difference between the non-combustible reference test and the treated test is much more significant. And if we go further into the test to opening 3 and opening 4, we see that the difference between the untreated test and the treated test becomes more significant. And going to opening 5 and opening 6, we see that the treated tests start to follow the same trend for the first 1 or 2 minutes as the non-combustible reference test. We also see that there is a stronger difference between the performance of the treated ceilings. And because of that, I want to use one of those plots to see if there is a correlation with the SBI test. First, just looking at the Euro classes, we have Euro class A, which is the non-combustible test. Then we have a bunch of tests that correspond to Euro class B, and then we have our Euro class D tests. And there we do see a clear deviation. But then I want to look within Euro class B and see if the phi values and the THR 600S values actually correlate with the performance in this bigger test. I'll start with the bottom curve, which was the best performance, and then go up. And we will see if there is a good correlation, we should see the phi values increasing. So this is the next curve, and then we have, so far so good, we have an increasing phi value with reduced performance. But then we have test C, where we have a low phi value, but not a very good performance relative to the others, which is indicating no perfect correlation. However, we do see that the other tests seem somewhat in line. Test F is also a bit odd. It has the worst performance of all tests, but it doesn't have the lowest phi value. And then looking at the THR 600 seconds value, also this should increase for every subsequent curve. And also here, so far so good, but then we see test C doesn't really correlate. But then the other tests actually show some agreement. So with some exceptions, there is some agreement between the SBI test results and the performance at a full scale. But a much more important question is, can we use the SBI test to achieve the results that we would desire in a compartment? and that will depend on the compartment. It will depend on the compartment size and also the occupancy, how much fuel is there within the compartment. But to discuss this within the presentation, I'll show this plot and explain the plot first. Here we see the distance from the compartment start, and the compartment start is on the right side of the compartment. And if we go on the axis, if we go upwards in the x-axis, we actually move towards the left of the compartment, which is a bit counterintuitive. And the plot shows the time at which 300 degrees was reached at the plate thermometers. And we see that 4.5 meters into the compartment, the difference between the untreated reference test and the treated test is not very significant, but this difference becomes increasingly more significant. And after 10.5 meters, we do see that the treatments have much more impact. And we think that this is related to treatments being developed to pass the SBI test, which has a relatively low exposure. And these low exposures can be seen more towards the end of the compartment. That's our explanation of the curves deviating much more on this side of the plot. However, close to the fire source, the risk of items igniting is actually not significantly reduced. And there may be compartments where we actually want to achieve that. So what we in such compartments want is to move this point to the left. We want to have a more significant impact of our treatments closer to the fire source. And there we can say that even very good SBI test results didn't really manage to do that. So we think there is a need for a new test next to SBI testing in case we want reduced risk of ignition of combustible items close to the fire source. And likely that test needs a higher exposure. To visualize the conditions within the compartment, we developed these heat maps, which I'll briefly explain. There are 3 lines in the heat maps, and they indicate different criteria. In black, we have our tenability criterion, which is a simplification. It's a conservative approximation of a more commonly used tenability criterion of 2.5 kilowatts per square meter heat flux. Then we have piloted ignition of wood and spontaneous ignition of wood. That means that if an object that is made of wood is positioned on the right side of this line, then we expect it to be ignited. And the same if a person would be located on the right side of this black line, then we assume that he would be deceased. We cannot assess the tenability criterion, but we can assess whether our spontaneous ignition criterion worked because we had ignition specimens made of wood in the room. Here we see the plots, the times at which these specimens ignited in the room with the dashed curves, and set against that is the time at which the heat map prediction thinks that the wood piece would have ignited. And we see a relatively good agreement with some exceptions between the experimental ignition times and the times of ignition according to the heat map. That indicates that our gray line here has some validity. Here we see the heat maps of all tests after 1.5 minutes. In test R, we have the most significant fire development. That's the untreated reference test. In the non-combustible reference test, we have the least significant requirements, least significant development. And in the treated test, we have a development that falls in between those two. Here we see the development after 6 minutes. In test R, the untreated reference test, the plot is completely red, and that holds also for test F. That indicates that wooden furniture would have ignited, and it indicates that we do expect flashover to have occurred by that time. In the other plots, we still see a lot of significant fire development, and likely if there was other fuel in the room, on the right side and the right half of the room, it would have ignited, leading to additional fire growth. What we also see is that the distance from the ceiling does matter, and that indicates that ceiling height also matters, because further away from the ceiling, there is less radiation, less risk of ignition. Before I end my presentation, I want to discuss test E and F. Both had impregnated panels, and both fulfilled class B. We had the same impregnation, however, test E had twice as much impregnation as test F, but the performance was very different. E had the best performance in many aspects, and test F had the worst performance. So that indicates that using more treatment than required can actually result in better performance. Another thing I have to mention of both of these tests is that the impregnated panels shrink significantly, leading to fall off in both tests. The shrinkage measured on the fire side was up to 12%, and on the far end of the compartment, it was up to 7%, which is much more significant than you would expect with regular wood, untreated wood. We also performed an SBI test of test F, of the specimen of test F ourselves, and here there was no fall off. And also behind the paneling and the substrate only contributed marginally to the fire in the SBI test. So we can say that the SBI test doesn't include integrity failure the same way as our compartment does. To indicate how these compartment tests can be interpreted, I want to discuss the fire scenario. We used a very quickly igniting fuel. Here we see the heat release rate of the fire pool in test A, and compared it to that of heavy sofa, a 3-seat sofa, and a pallet with 36 crates of plastic bottles. And we see that the heat release rate is actually relevant, but on the severe side, but the fire growth rate is much faster than what we would expect for regular fuel. And that needs to be taken into account when interpreting the test results. Further, I want to indicate that there was quite a severe scenario. The ceiling height from the fuel was 1.9 meters, which is what we considered common. And as I mentioned before, the beam protrusions and the beam spacing was chosen to be unfavorable but realistic. So we do think we have a relatively severe scenario. Then I go to the conclusions. The test with a non-combustible ceiling experienced slower temperature developments than the treated and untreated tests. This resulted in more tenable conditions and significantly less risk of ignition of items at a distance to the fire source. Then regarding the treatments itself, BS1 D0 treated timber ceilings can lead to less external flaming than untreated ceilings in large compartments. BS1 D0 treatment has had significant impact beyond 6.5 meters from the fire source. However, at 3.5 meter distance, the impact was small. This reduces the likelihood of extended ceiling ignition and consequent rapid fire growth in very large compartments. But it only marginally reduces the likelihood of ignition of combustible content in close vicinity and its consequent impact on the fire growth. So we still can have, we think, quite significant fires. However, because the ceiling needs to ignite the fuel and the fuel combustion needs to grow, we think this mode of fire growth is slower. And we also think that increasing the ceiling height will reduce the likelihood of items close to the fire source igniting. So going to the last set of conclusions, within the surface class B, the SBI test results showed partial agreement with the performance of the compartment tests. However, a good performance in SBI testing does not necessarily lead to less ignition risks in the vicinity of the fire source. In 2 fire tests, impregnated panels experienced loss of integrity, leading to fire growth in the later stages of the test. Such loss of integrity was not captured during the SBI tests. And then lastly, the quantity of impregnation had a significant positive impact on the compartment fire performance, despite SBI tests indicating that the worst performance panel still fulfilled Class B, Euro Class B. Lastly, I want to discuss our recommendations for future research. Yes, treatments can reduce the external flaming. It can reduce the risk of extended flame ignition, sealing ignition. However, we also see reasons to apply more treatment than currently required. And the questions become how much treatments, how much of the treatment and which test should we do to show compliance. And in addition to that, we want to look at, or we want to recommend future researchers to look at combinations of such measures. So let's say we have an increased sealing height. How effective would treatments then become? So that was my presentation. Thank you very much for listening.
Thank you, Daniel. That's a very interesting presentation. Welcome to ask your questions in the Q&A, and some of you already have asked some questions. We did get a question during the presentation that you answered. Johan, can we just get back to that? First of all, it was a question about wind direction in the different tests and the figure value.
Yes, so the question was posed as if the direction of the wind could influence the figure value, and that was especially related to test C. But the figure value is determined in an SBI test indoors, so not related to our compartment tests.
Right. I became curious about you compare the figure value and the SBI test, and if I want to choose between different products, can I get those data from different products, or how can I use it as a building designer, for example?
Sorry, how can you use?
Are those data available for anyone to see for a specific product what the SBI and the figure test has shown for that product?
No, you can only see the class. The class is what is delivered, and so to see that you need to have a test report which is classified. So no, all of these are from a public viewpoint identical. They're the same class.
Okay, thank you. And yeah, we have a question here. You mentioned impregnation. Was it a surface treatment or impregnated throughout the thickness of the product?
Yeah, so that I guess I wasn't very clear on that. So we had a mass timber panel, and then that was protected with an impregnated panel, and the impregnated panel was 23 millimeter thick. So it was added to, it was protecting an unimpregnated mass timber specimen, but the panel itself was fully impregnated.
Okay, thank you. And did you conduct the SBI test on all the surfaces treated, or on the impregnated one?
So the SBI test, the results that we got were from the mostly from manufacturers, but then it had one exception, and that was test F, which we conducted ourselves.
Right. Was that the test where you added more impregnation to the?
Yeah, so it was less impregnation. Yeah.
Less. Okay.
Yeah.
The intent was to actually get a C class, so we could have something which differs also from a public standpoint.
Right.
But when we did the test, it indicated class B, also that.
Right. Okay, thank you. And here's a question about regarding tenability. Did you compare the smoke layer height or visibility in each case, or how did you?
No, tenability. Just the visibility and the smoke layer, that's not actually assessed in the tenability criterion. It's only the thermal radiation tenability criterion of 2.5. It's not the 2.5 kilowatts per square meter criterion, but something that is somewhat similar. So we ignored convective cooling because it had high uncertainty. So we have an approximation of this radiative tenability criterion.
Right, thank you. Yeah, we also get some questions about design goals with fire safety, and I think that varies between countries, of course, what the building code states. But what are the main things that you want to achieve when you use a fire retardant in a ceiling, for example?
Well, the design codes have the building codes usually have functional requirements, which indicate the function of the building, and in all cases you want people to safely egress. So that's actually something that will be a requirement in all countries. So in terms of life safety, the first thing you want is give enough time for people to leave, and normally it's not that much of an issue in office spaces where everyone is awake. We usually talk only about residential buildings. However, if you're asleep, then you would have, and this kind of fire would grow in your apartment, then you would have a problem in any case, whether you have a concrete surface or a CLT surface. But then what's relatively new is and that's why I mentioned the very large compartments. If you have interconnected floors, big atria, and it's all exposed wood, but then we really need to consider how fast is the fire going to grow, because we cannot have such a fire that would ignite everything if multiple floors, and that's why so even though and the results do not indicate a significantly improved performance close to the fire source, far away from the fire source, it seems to matter a lot. And for the for bigger compartments, like much bigger than we normally design for, it becomes quite important to either use treatments or something else. Well, preferably make smaller compartments, but sprinklers help, ceiling height helps, and reduce ceiling protrusions.
Yeah. Right. Thank you. When looking at your data, I think you had one test with no treatment and one test with non-combustible sealing, and they were quite far apart. and then all the other tests they ended up somewhere in between. The difference between a treated timber building like this, a fire retardant treatment, and a non-combustible roof, it seemed to be quite large. Someone stays here. Do you think? How should we interpret those data and those this comparison?
Yeah, so I think if we look at the functional requirement of buildings, we want people to safely egress. So we have to look at it as a separate case. So we if you can achieve it with, for example, a mass timber structure, as long as you provide enough time of egress, and yes, impregnation will help with that, especially in a bigger compartment. Yeah, so how to, and I would say, and then the comparison, and I know this comparison is in the project, but maybe we should see it as a message to not design a mass timber building the same way as we would design a concrete building, especially if we build these maybe 5-6 story compartments, and need to consider, okay, what if we got a rapid fire spread? How can we use impregnations and things like how much fuel is expected to be in this room, or it depends on the occupancy type.
Right.
I guess the main message is design it with the mindset that it is not a concrete building, but it is a mass timber building that can use treatments, sprinklers, or limit the compartments, as long as you won't get a high consequence fire event.
That's also something which is reoccurring in many of the aspects with mass timber buildings, that you design them based on a framework which is developed for non-combustible structure, and we've shown over and over again that there are solutions. There are ways you can design mass timber buildings also for large compartments, but you need to use your engineering skills and actually look at the building you're designing, and how to fulfill the functional requirements rather than prescriptive ones.
Right. And also, I'm thinking about the fire service intervention, because they may be in the building for way longer time than the evacuating people are. So I think, from that point of view, I think the surface may differ more for them.
Well, I think especially if you consider a fire that grows and stays local and grows more and more, or maybe travels, that will be a better scenario than a huge compartment leading to flashover, because you cannot really fight a flashover fire in a huge compartment. Yes, just for them, I think that's the main difference. Try to keep your fire local, and it's not only about safe egress.
Right. Thank you. We have some follow-up questions coming in about this test C and the figure value, and whether the different wind directions may have affected your correlation between your measurements and the figure value.
Yes. Well, yes, the wind puts an uncertainty, especially between among the Class B treatments. However, we did have a few tests where there was absolutely no wind.
Right, thank you. And picking up some more questions about charring, for example, we have a few questions. Did you measure charring in the study, and how do you treat that data or in your analysis?
I know we measured charring. I didn't present it because it like within the class B specimens, it didn't really result in a big difference. And then yes, class A, sorry, an untreated reference has did char more at the far end of the compartment, but not more at the fire side. And I feel like that those results are quite logical and didn't really feel like it didn't make it to the end of the presentation in the end. Mm.
Yeah, right. But maybe we can learn more about it in the report.
Yes, yeah.
Which is not ready yet, I can add. It will be published early next year, I hope.
Yes, yeah.
Yeah, and you've been talking about different size of compartments and also different ceiling heights. You tested it was in 1.9 meters. I actually measured my ceiling here was 2.6 meters. And do you think that we need to differ test methods and building code demands more depending on the compartment size and the ceiling height and such?
Well, the ceiling height, I feel like we don't know too much of, but it's going to be very important. So 1.9 meters from the fire pool to the ceiling. So we imagined if you have a sofa, then you're half a meter higher, and then a low ceiling height. So this distance would be what we consider the minimum, or yeah, a small distance, but and still plausible. But if you look at fire plume heights, and we have this discussion mainly also because of the contributions of Tian and Frick, that flame heights, they can be up to 3.5, 4 meters, but you need so much more energy to if you increase the heat release rate by a factor of 2. The flame height is not increased by a factor of 2. It's only going marginally up, and at some point you can say, or your ceiling is so high that the ignition is unlikely, and then especially if you then combine it with treatments. I think if we normally look at open space compartments, ceiling height of 4 meters isn't unrealistic. But then you need a significant fire source to actually even get a fire plume that reaches the ceiling. And then if you have treatments, it would likely significantly improve your scenario also for closer by. And in addition, it's something I didn't mention in the presentation, but when we picture these heat maps, in the heat map, height, distance from the ceiling matters a lot. So if you have a higher ceiling, the risk of ignition of fuel on the floor from the ceiling radiation is drastically reduced as well. And so you basically, by increasing the ceiling, you reduce the interaction between the ceiling and the floor fire in 2 ways. So it less likely ignites, and if it ignites, it has a reduced risk of ignition of fuel on the floor. So yes, maybe in most scenarios, like if you have ceiling heights of 4 meters, maybe it's actually not that much of an issue at all. But it's something I'd like to study in the future.
Yeah, sounds really interesting. We get some questions about integrity and different treatments. Did you compare anything? Did you compare your treatments with the K210 classification?
No. and I think officially K210 would be a layer that protects timber for 10 minutes. So in test E and test F, we added a layer impregnation. And it was 23 millimeters thick. It did fall at some point, but normally with K210, we have 10 minutes of fire resistance testing. It needs to withstand. That would equal 7 millimeters of charring. This board would very likely would have passed the K210 class. But then this fire is not is a lot more severe than what you would expect in a furnace test for 10 minutes.
Yeah, right. So it's not really comparable.
No, not. But the panels of test E and F would. I'm convinced they would have passed K210 easily. Yeah.
Okay. Well, thank you. One question is it's not within the scope of this project, but do you know have there been any comparison between regulations in different countries regarding surface in
Yes,
wooden buildings?
I think the most extensive work is done by Birgit Östman, published in 2022. And it shows a global overview of regulations such as fire resistance and surface treatments. Yes, and then there are some other studies, but they're not as extensive.
No, but we can recommend. I think Birgit is listening now, so maybe we can add a link to that report. That would be nice. I was thinking about, now you looked at large compartments. Now, at least in Sweden, I think most timber buildings built today is residential apartment buildings in like 4, 5, 6 stories high. And can we learn anything from this project when we talk about treatment in ceilings in compartment buildings in Sweden today?
Yeah, I think so. When we look at our fire, we went up to 2 megawatts very fast. It requires, even with the ultra fast fire growth, it would require more than 2 minutes, I believe, to reach that level. Then 2 minutes, you need this may equal like a Christmas tree burning, maybe. Yes. In that scenario, you will always have a problem in a small space. You don't want to be in that space in any case. And then whether the ceiling ignites after that point, in a small room doesn't really matter. You wouldn't really survive if you're asleep. Then you have a problem. If you're awake, you can easily escape a small room unless it's blocking the door. Which in any case, it seems to be your risk of life safety seems not so much dependent on whether your ceiling ignites, but then maybe in larger compartments where, but still a compartment. If you're awake, you will likely have enough time. I mean, it's very unlikely that you won't get out unless something is blocking the door. But then you have a problem in any case. Yes, I think what we want to look at is the test of code red, sort of really showed, okay, we have this, we can have an accelerated flame spread in a large compartment, and we try to respond to that, or try to find to see if we have a solution now to that. And I guess the answer is partially it's a solution. Yes. or otherwise like a combination of treatments and sprinklers would reduce risks, but mostly just try to avoid enormous compartments. I would say until we have either or be very sure that there is no fuel. I guess if a compartment has a very sparsely spaced fuel, maybe hallways or maybe atria, it could be safe. But we didn't go that far. Like it's quite an extrapolation from the test that we did. But it's just we just have to say that we need to pay attention. Like we cannot build infinite spaces. We need limits.
And we need to again use our engineering skills when designing the buildings.
Yes, always a true word. Yeah, and I'm very curious really about this apartment building. So maybe that's a future project because you mentioned 3.5 meters as a within 3.5 minutes you didn't see much difference between the untreated wood and the treated wood, and normally a room in a residential apartment is usually within 3.5 meters from a fire origin. So it seems to be an interesting case to look into more, I think.
Yeah, but if you have a 2.5 or 2 megawatt fire in a room of 3.5 meters, you shouldn't be in that room. Like
but I may be in an adjacent room. So you talk about future research, but I think to the audience here today, any recommendations that you would like to give them? You talked about use your engineering skills, you once said, and that's a good recommendation. Any more words on how to use the results from your work?
Yes, well, I guess that's why we wrote this chapter for guidance. So a lot of we don't have thresholds, and that's where it becomes an issue. So we're not regulators. We cannot say, okay, but this is not allowed and this is. But we have some quite strong indications, like the heat maps actually show a trend, like the further you go down, the less risk there is, and I feel the heat maps can actually used at the moment as an argument to, like, if you have higher seating, get I guess you can you can use it in multiple ways. So you can try to replicate the scenario in a model, and then model it for the real compartment, but just also more qualitative on the heat maps to indicate the effect of ceiling height or distance from the ceiling. Okay, maybe we have 4 meters ceiling. The fire plume that we expect from a sofa is maybe 3 meters, which already reduces the risk of ignition. Then if you have impregnations, that reduces it even more. But then a 4 meters ceiling that is impregnated, radiating to combustion, to combustible elements on the floor, that's also a much lower risk than we saw. So you can use it as a reference point. Okay, but our building is actually has a much less severe scenario as what is tested, and yeah.
I'd also like to add that I mean the one of the key messages in this report is that don't consider a B class from an SBI test an insurance. We cannot say that it's not a guarantee that you won't have rapid fire spread. In most cases, you will have a good effect, but then again, set it into the specifics of that building. It probably won't take more than half an hour for a designer to come up with if this is a good solution or not. But you need to do that, not only say it's treated, it's class B, it's fine.
Right.
And maybe I want to add, because we see a lot of buildings, we review building designs. There's also a difference between a solid surface and a surface with a lot of a ceiling with a lot of small members, and the small members have much more surface. And if it's if there's small members next to each other, they radiate to each other. It creates a whole other situation. It's pretty much another system. And when it comes to SBI testing, you do not test a surface, but you do test this system. So you would also need to consider that doesn't necessarily fall within the regulation. So you cannot something that is tested on a flat surface apply for very small timber pieces in the ceiling.
Yes. Thank you. We get a message here from Birgit now. The report National Fire Regulations for the Use of Wooden Buildings Worldwide Review 2020 is available at the divaportal.org. Thank you, Birgit. I can recommend that report. Any final words from you, Johan, Daniel?
No, nothing I can think of. But thank you for listening.
Yes, and there will be a quite extensive report released in a few weeks. It's just out for review at the moment.
Yes. Yeah, that will be really interesting to see the report. Thank you so much for your presentation and your work and all your good answers to our questions. And I wish you a Merry Christmas, of course. And
yes, you too.
Thank you. So I'm just going to wrap things up here and tell you about more what's going on at Brandforsk. First of all, I like to remind all of you about our fundraising. If you are not already supporting organization, please become one. We need that to keep this work going on. And we have some upcoming webinars. This was the last for this year, and we did plan a webinar next Friday, but we had to move that. But it's now dated to. It's not planned to February 9th. No, sorry, February 16th, and that's a webinar in Swedish. And you can always get. Learn more about what's going on here. Follow us in LinkedIn or sign up for our newsletter, and you will always get the latest news. And we also have a podcast that we started this year. It's in Swedish, talking about fire safety in especially in residential buildings and for elderly people right now, but sometimes also about other things. And if you don't know Swedish yet, you can learn both about fire safety in this podcast, but also learn Swedish. And thank you, of course, to Daniel and Johan. And I also like to thank my colleagues, Francis Eurenius and Matthias Hammarin, that both work very hard at producing these webinars. Thank you very much. And that's all for today. So I would like to wish you all a Merry Christmas and a Happy New Year. And I hope to see you next year.